If they're over that, they also need to know because they could be losing money. It means they're putting more in their products than what they're accounting for price. So it's a really useful tool. We use these for grades. I'm going to show you an example with grades, how we do that. So, yep, chapter 16 on confidence intervals. So in here in this chapter, we cover the reasoning of statistical estimation. This is all about making inference or estimating plausible values. The margin of error and confidence level. How do we put all these pieces together to come up with a confidence interval? Sometimes we call them statistical intervals for a mean, so for an average. And then how confidence intervals behave. So what are their properties? So as you know, we take a sample from the population, often because we just can't get all of the entire population and measure those. So we take a sample, we collect that data, and we make sure it's a representative sample. And then we can make inference about the population. That's the process. So we take a sample. So in confidence intervals that I was just describing about, let's say, potato chips, Mr. Potato Chips Company, we could take a random sample of, say, 15 bags of chips and then measure them, right? Instead of taking all the chips, you would destroy all the products too, which would not be good. So you would take a sample and then measure them all and then come up with a confidence interval. And that's what this chapter is about. We'll see how that works, how we do that. So the conditions, this means we are making assumptions that the sample is a simple random sample. So that means equal chance of being selected, right? Every unit, person, subject in the population has an equal chance of being selected. There's no non-response or other practical difficulties. We're assuming everything's good. And the population is large compared to the size of the sample. The variables that we measure have an exact normal distribution for this chapter. It's exactly normal. We're going to see in future chapters, what if it's not normally distributed? How do we deal with that? And we'll see how that's done later. And we don't know the population mean mu. This is the whole point. We want to estimate the population mean, right? And so just to remind you, sometimes I call the population mean mu. I call it the true mean, meaning it's the mean of every measurement in the population of interest. Okay, and in this chapter, we do know, though, the standard deviation value, sigma. I'm just gonna, so we don't know the population mean mu, but we do know in this chapter, at least, the value of the standard deviation sigma. Later on, these conditions will change. We will see how to deal with data that is not normally distributed, and when we do not know the mean nor the standard deviation. So that's later, but for now, this is what we're looking at. So we have a normal population. We took a simple random sample from the normal population, normally distributed with mean mu, standard deviation sigma. We don't know mu, but we know the value of sigma. And when we make these assumptions, we basically know the value of sigma based on previous samples from that population. It's usually from prior studies. So let's say we have an example of grades. So let's say we have a class average, right? And let's say we only have this information. So let's say we have the standard deviation I know is usually 9.2 based on previous years. I have a random sample of 25 students. That's n. We call that with a little n, lowercase n, equals 25. And the sample mean, that's x bar, is, let's say, 676 for the overall course average. So how can we estimate the total class average? I only have 25 students. Let's say there's 100 students. How do I get the full class out? How can I estimate it based on a sample? Right? So this chapter will help us solve these type of problems. Just to be clear, standard deviation, this would be sigma, right? Random sample n, so that's our parameter there, n. And the sample mean, this is x bar, sample mean. Okay, so sample mean is x bar. Population mean is that mu, right? The Greek u. Okay, so a confidence interval is a range of values that could contain the population mean mu. So it has a minimum, a maximum, and any value in between could be the true mean. And it's a range of values that we use to estimate. So every confidence interval has this structure. It's the estimate plus or minus. You can see that plus or minus there. A margin of error. So if we think back to Mr. Chips, it was the random sample could be, say, well, we figured it would be good if it was plus or minus 2, right? Then, you know, because we know that it's not going to be exact. The sample won't be exactly equal to the mean. So we have this margin of error, we call it. So it's plus or minus something to sort of account for the fact that it's a random sample from the population. We know that there's going to be something, we know we're going to be off a little, and that's what that margin of error is. So we add it and we subtract it from the statistical estimate. All right, to define a confidence interval at a given confidence level. So it has two parts, the estimate and the margin of error. We also have the confidence level C. So if we think about it here with a picture, we know the shape of this is our bell shape, normally distributed. And we know that if we were to do, if C is 95%, let's for an example, let's put C equals 95%. Then this yellow region would be 95%, and each of the tails would be 1 subtract, so this would be 0.95. I've got it in a percent, but we could also say equals 0.95, right? And so 1 subtract 0.95 divided by 2, and 1 subtract 0.95 divided by 2. So we know then we'd have 2.5% in each of the tails. This would be our confidence level if we wanted to be 95% confident. Do you remember the empirical rule where if we were 95% of the central values, what did we have to do to the mean? It was plus or minus something times the standard deviation. Yes. Put it? 3? 1? 1.2. Yeah, it was 2, right? So to get 95 for the 95% rule, it was for the 95% rule part, it was mu plus or minus 2 to get 95. Ring a bell? Yep. So if we do mu plus or minus 2, it turns out if we use the table instead, you know, our table here, if we use this instead of just using 2 from the empirical rule, it turns out that it's actually 1.96 to be more precise. So it's actually 1.96 here and subtract 1.96, so negative. So it's plus or minus 1.96. If we're just using the empirical rule, just throw in 2. But if we want to be more precise, we use 1.96, which you agree is really close to 2. It's just a little more accurate because it's coming from the table. So if you were to look up the the value of Z, reverse lookup, the value of Z that is closest to 0.025, you're going to get negative 1.96. And because of it being symmetric, this would be the 97th 0.5th percentile, because that would be 2.5%. So that would be positive 1.96. So instead of 2, this is an estimate, but we can use, using the table, we would go mu plus or minus 1.96. Well, I'm running out of, it won't let me write right there. Let me see, mu plus or minus 1.96. All right? Right, so we know the confidence level we want. Let's suppose we want 95. And quite often that's what our confidence levels are. We can't be 100% confident for many reasons. One, it's a random sample. We would never be able to know for sure 100%. If we could, then we wouldn't be estimating anything. But also we can't do 100% because of the theoretical value. If we wanted 100% of the bell, like for the whole thing to be yellow, we need to go from negative infinity to infinity, which that our confidence interval would be mu plus or minus infinity, which you're basically saying it could be anything. So we can't use 100%. So we go with a 95% because we know it's a random sample and we know we're going to have some error and we know that there's some uncertainty. So that means that 95% of the time, we're going to be right. It means the confidence interval will contain the true population mean mu. But 5% of the time, right, when you add up the green portions, the green areas under the curve, 5% of the time we're going to be wrong. The confidence interval will not have captured the true population mean. Okay, so what are we confident about? We're confident about the method in which we construct this confidence interval. It's based on repeated sampling. So if I went and took a sample and then I took and calculated the mean and constructed a confidence interval and then went and did it again and keep going, just like the sampling distributions from chapter 15, then I would have 95% of those of all possible confidence intervals would contain the true mean, but 5% of them would not. All right, so here is our values. This is going to be provided for you. So if you're doing a 95% confidence interval, so 95% confidence is 1.96. So you don't have to do the reverse lookup. And this is a value I recommend memorizing because it's used so often in our confidence intervals. If we want a 95% confidence interval, just know the confidence level C that goes into the margin of error is going to be 1.96. Okay, 1.96. This will be provided to you. It actually comes to you at the bottom of a table that we're going to have for our exam. Mm-hmm. Yeah, that's a really good observation. We're going to talk about that. Remember how I said we're going to talk about how confidence intervals behave? It turns out, so the question is, why do we have a higher number for the higher confidence level, right? Because that's going to be giving us a wider confidence interval, which is not really good, right? But we can see that as the percentages increase, the confidence, the Z values increase, right? And that's sort of the trade-off. There's a trade-off. So if we were to build, say, a 90% confidence interval, that would be great because it's a 1.645. It's good. It's a nice smaller number, but I'm not as confident. So you have to give up something to get the narrow confidence interval. But if I want to be more confident, let's say I want to be 99% confident then I'm going to have to use a higher value for Z. I'm going to have to use a 2.576. So there's a trade-off. You have to give up either confidence or give up the narrow confidence interval, a smaller margin of error. And why does that happen? It happens because of here, as we move here to get higher values of Z, this is going to shrink. The green section shrinks to put more probability in the middle. Yeah. So the most common ones is the 95, but we also see 90 and we see 99. All right, so those are, but know the 95. It's sort of the happy medium. It's sort of, you know, it's not, we have a nice amount of confidence, but it's not 99 with a higher value of Z. And you'll see more what that means when we put it all together. So here's all the pieces we have here. We have here, this part here is the margin of error. And it consists of the Z star. Now we call it critical value Z star. And you might be going, Z star, why is there a star? It's the same as our Z scores. It's just in the context of a confidence interval. When you see a critical value Z star, you just know, oh, that's because of the confidence. It's a confidence level for the confidence interval. So we just put a little star there and we call it Z star. And so let's say we want a Z star of 95. We would use Z star equals 1.96, just like the table told us on the previous page. So it's the Z that goes with the level of confidence. So if you want a confidence C of 95%, then we use 1.96. This here is the population standard deviation. And this here is the size of our sample. Our random sample. And this here is X bar. What is X bar? It's our sample mean, right? It's the average that we calculate from the sample. If we look at just this part here, so the sigma over square root n, remember that's the standard error of the sample mean. That's from chapter 5, this here. Right? Remember that if you refresh from chapter 15, if you refresh and review that, you'll see that sigma divided by square root n is the standard deviation of the sample mean. Remember how we have the sampling distributions, that's the title of that chapter that we just covered. And so we put all these pieces together. So it's X bar plus or minus Z star, critical value, we call it Z star, times sigma divided by square root n. So when we put it all together, I'm just going to show you, we'd have X bar subtract sigma, all this that's multiplied to X bar plus sigma, oh, I forgot the Z, Z times sigma over square root n. So this would be our minimum value. Right here is our minimum to our maximum. Okay, and the true population mean can be any value between the minimum and the maximum, including those. Okay. And we'll do lots of examples to see how to put this together. So let's say we have the class average example. So let's say we have only the following information. We have a sigma standard deviation, that's sigma equals 9.2. We have n equals 25 students, and we have the sample mean equals 76. And so we're going to calculate. So let's calculate. We can put one together right here, a 95% confidence interval. We're missing one piece. So it's going to be x bar plus or minus z star. You don't have to put the star there, but I do, because then I know it's a confidence interval, and that is associated with my level of confidence, multiply by sigma over square root n. So everything to the right of the plus or minus is our margin of error. We have everything. We have x bar, we have sigma, we have n. Oh, but we are missing one thing. What value of z should we use? Critical value z star. Anyone? Yeah. 1.96. You've got it memorized. Awesome. Yes, so our z star, because it says here 95% confidence, we want to use z star equals 1.96. So we have everything we need, right? That goes with that. So if it says 95% confidence, it's z equals 1.96. And it just goes into the formula just like that. So we can go 76 plus or minus 1.96. Multiply that by 9.2, that's our sigma, divided by the square root of 25. That ends up equaling 76 plus or minus, and we can get a margin of error here. I get it to be 3.6064. I'm carrying 4 decimals because this is still an intermediate step, because I still have to subtract and add it. So that ends up equaling, if I go 76 subtract 3.6064 to 76 plus 3.6064, that's going to be equal to, so if I subtract it, I get 72.4. That's my lower bound, to 79.6. And you can check that. See if you get the same. So sometimes we write it like this, 72.4, comma, 79.6 in brackets like that. The square brackets are mathematical for meaning include the endpoints. So what does that mean in a picture? If we were to draw the number line and we started here, this would be 72.6 to 0.4 to 0.6. That would be our confidence interval right here. So all the values from 72.4 to 79.6 could be the true class average. And the mean is somewhere right here, which was 76. So the width of the confidence interval, how wide is it? The width of the confidence interval is going to be 2 times 3.6064, because the width is always The width is always 2 times the confidence interval, the margin of error. So this here is a margin of error. I'll call it ME. And here is the margin of error because we subtract and add the margin of error, right? So it's 76 plus the margin of error, or 76 subtract the margin of error. When we subtract, we get 72.4. When we add the margin of error, we get 79.6. So the width of the confidence interval would be, what's the width? Would be equal to 79.6 subtract 72.4. What do we get? You can also get this from multiplying 3.6064 times 2, or we can just do 79.6. You can work it out to convince yourself as well. Check to see what you get. The width I get is 7.2. That's the width of the confidence interval. So we've constructed one of many. We'll have lots to do. We'll construct lots of these to get lots of practice, right? So you have your x bar, that's your formula, x bar plus or minus z times sigma divided by square root n. Everything to the right of the plus or minus is our margin of error. I'm calling the margin of error ME, all right? And the width of this particular one is 7.2. So we would say that in conclusion, you would say a 95% confidence interval for mu is 72.4 to 79.6. So in words, again, we could say a 95% confidence interval for the true class average. The true class average is between 72.4 and 79.6. So it really is a great way to get an estimate for the true population mean when you can't measure everybody in the population. Just take a random sample, calculate a confidence interval. Okay? And why 95%? It's 95% because we used the corresponding Z, that, right? All the values between negative 1.96 to positive 1.96 is covering 95% of all the samples. Right? All right. The confidence level is basically what I was just saying. It's the overall capture rate. So if it's the overall capture rate, if the method is used many times. So let's say I go out, I get another random sample of students, 25 students, calculate their mean and construct a confidence interval and do that again and again. And I keep with the computer, I could grab 25 more and 25 more, and it's always with replacement. You put them back and then you can get 25 other, the population has to be large enough to keep getting 25 students. And you do that many times. And you use Z equals 1.96, 95% of the time, those confidence intervals will capture the true population mean, mu, but 5% it will not. If I did the same thing, and it's called repeated sampling. Let's say I repeated the sample method and constructed all possible confidence intervals, let's say 90%. So 90% of the time I will have captured the true mean. But how much of the time will I have not? It would be 10% in that case, because it has to add up to 100. right? That's what the confidence level means. And when we're interpreting it, what are we confident in? We're confident in the success rate of the method. Really important to say that we're confident in the success rate because of the way we constructed it. And we don't know, when we construct a confidence interval, we don't know, like this one here, we don't know if we are right, if we've got a good one or not. We can just say that we're 95% confident that the true grade is between 72.4 and 79.6. We're 95% confident, but it could also 5% of the time it could be wrong. Right? So, and we don't know because it's a random sample. So hopefully we're not unlucky. We could be unlucky. We're 95% of the time, we don't know if we've captured it or not, or one of the lucky 5% that miss. So we say we are 95% confident that the unknown population mean that we're trying to estimate lies between the two values. And we can formally say we got these numbers using a method that gives correct results 95% of the time. So you might see, like in the media, like a news network like CBC, they'll do a study and they'll have a disclaimer at the bottom saying, this is accurate 19 times out of 20, which is 95%. One time out of 20, it will be wrong. So 19 times, and it will always say that 19 times out of 20, this is how accurate we have, right? Now you know what that means when you see the results on the media or wherever you're looking. So here's the interpretation. So if I was to construct, how many do we have here? 3, 4, 5. I have 25. I have 25 here. And to give you a visual, if you look at these, all the blue confidence intervals. Now remember, we only construct one, but we have to think about it being based on many, many, many samples. Let's suppose we repeated this many, many times, and that's the interpretation, that's the correct interpretation. So you can see if the true mean mu is right here. Oh, let me grab a color. If the true mean mu is right along that line right there, the black line that goes down the center, and I construct the first confidence interval, then you can see that I'm crossing the true mean line, right? And you can see, in fact, all of the blue ones are crossing the black true mean line, but this one right here, as they're saying here, this interval misses the true. All the others capture it in the range of values, but the red one does not. And you never know. There's no way of knowing if we have an unlucky one or not. That's why we have the disclaimer. This method is accurate 19 times out of 20, right? Yeah. So that's the correct interpretation. It's a measure of uncertainty. So how could we get a small margin of error? So the margin of error is the critical value Z star times that. So how could we get a smaller margin of error? What could we do? What would need to happen to make this smaller? Well, one way would be to decrease we could decrease Z star, right? If we decrease Z star, we get a smaller margin of error, which is good. Small, you want a narrow confidence interval. You want to zoom in and have a very precise But the problem with that, as we discussed, is there's a trade-off. We're going to have less confidence. So we would be capturing it, we would be confident 90% of the time, let's say, but 10% of the time we would be wrong. So we're giving up our confidence to get a smaller Z value, right? What's another way to make this margin of error smaller? Yes.
Probably get a smaller margin of error with a higher percentage based on knowledge of what it's in the past. So like if you know that like, for instance, like London snowed this much as Reno November, you could probably have a higher percentage chance that it would snow that much this November.
Yeah.
Error. More certain on what it past year.
True. That's very true. And based on past studies, that lines right up with this. We could decrease this because we would have more certainty on the standard deviation of the past. And that's basically based when we know the population standard deviation, which we do for this chapter at least, that's based on prior knowledge, past experience. Previous studies, right, have told us that. So we could do that. The third way, there's one more way how we can make this number. Remember, the ME, the margin of error, is a number. How can we make it smaller? There's one more way. Increase N, yes. Increase N, it's not decrease because we're dividing by the square root of N. And therefore, we need to increase it to get that quantity smaller, the whole quantity. And that makes sense in words too. Like just think of the logic of that. If I get a larger sample, I'm going to have more information and it's going to be a smaller confidence interval, smaller error. So these are ways to decrease the error. Yeah. No, it can actually, it decreases it. So if you think back to chapter 15, as we increased our sample size, right, we get closer to mu and the standard deviation actually decreases because the standard deviation of the sample distribution is sigma divided by square root n. So it gets smaller as n increases. So we have control over that. If we have the time and the money, this is the one we have the most control. This one here, sigma is hard to control. Like it is what it is. It's just based on previous data. And we don't have a whole lot of control over the Z either because there's a trade-off. It's that we're going to have to give up some confidence to get a narrower or a smaller margin of error. So it's a trade-off. So let's look at the temperatures example. I collected some temperatures for March 17th, which, does anyone know what March 17th is? We celebrate this worldwide. Yes? St. Patrick's Day. So there was one year, quite a few years ago now, where it hit temperatures something like 25. It was just, there was definitely no university classes that day. It was too hot. It was the opposite of a snow day. Anyways, all you could see was green in the whole city. But I decided to get some temperatures for St. Patrick's Day over 10 years, and I collected it, and I got the standard deviation to be 2.5, and the average was 9 degrees, because it's not usually near 25. That was definitely an outlier year. But 9 is usually the average. And we assume that the standard deviation is about 2.5 degrees Celsius. So we can do this. In fact, this is what they do. The meteorologists will construct lots of confidence intervals. And so what is the value of critical value, that Z star, we call it, that can give us a 95% confidence interval? So what would be our confidence level C? What would be the Z that corresponds to that? It's just like a Z score. Think of it as a Z score if you want, but we put the star there because it's the confidence interval. context. What can we use? We said it earlier. Yes? 1.96, it's a great number to memorize. It's a good one. Good. And for this, we can go, what is the standard deviation of the sampling distribution? So it's not the margin of error, it's the standard deviation of the sampling distribution. Can anyone tell me remember what that was from chapter 15? Give you a hint, it's a quotient. Anybody? It's part of the confidence interval formula. So I'll put the whole confidence interval formula up here. That's our confidence interval formula. That's the confidence interval for the true mean. What is the sampling distribution of the sample mean? Yes? N, you got it. Yes, sigma divided by the square root of n. So it's this. So that we just plug in 2.5 divided by, what's our n in this case? Yep, 10, yes. So I took for 10 years. 10 years was my sample. And I ended up with 0.79. And then it says, what's the margin? So I'm doing this in pieces, which is good because then you can see how this is all built. Now the margin of error is both A and B together. It's all of this. So this is the margin of error, right? Because another way to do this equals X bar plus or minus the margin of error. So the margin of error is all this part right here. It's the Z times the sigma divided by the square root n. So I'll just bring that down so we can see it all. This is going to be 1.96 multiplied by 2.5 divided by the square root 10. I mean, you could just simply go 1.96 times 0.79 if you want. And we get 1.5484. Right? Everyone sees all the pieces? It's like finding all the pieces to the recipe. And then I'm pretty sure I'm going to be putting this all together. So we have 1.96 is our Z, our sampling distribution, standard deviation for the sampling distribution, X bar is 0.79. We put it together to get the margin of error, 1.5484. Finally, let's calculate it. So this is a confidence interval for all years, not just the last 10. So a confidence interval So we're going to say a confidence interval for the true average temperature for March 17, because remember, I took a random sample of 10 years, but I can then go what is it for all time, right? And we can do this. This is going to be X bar plus or minus, and we can just put all the pieces together. It's going to be Z times sigma over square root n. That's our margin of error. That equals 9, right? We had 9 degrees Celsius plus or minus 1.5484. 0.84, because we got that from the previous, from part C, which equals 9 subtract 1.5484 to 9 plus 1.5484, which equals 7.4516 to 10.5484 degrees Celsius. We'll put our units in. It's going to be 7.4516, comma, this is just another way of writing it, 10.5484 degrees Celsius. I can put degrees Celsius here too, degrees Celsius, there, with a comma. So all the values between 7.4516 to 10.5484 degrees Celsius could contain, any of those values between those two numbers could be the true average for March 17. It's a good estimate, especially if you've taken a random sample of 10 years from the past. So chances are it'll be that. If it isn't, then, right, 95% of the time it will. We'll be right. 5% of the time we won't be right. Could end up with an outlier because of the whole nature of it being a random sample, right? Says that we could be wrong. But it's a really good estimate, and that's how we do them for temperatures, for quality control, like I said, with Mr. Chips, for checking, and for fuel costs. So here's the fuel cost example. We have, imagine you only have the following information for the fuel. Let's say we have a sample mean of 330.6, standard deviation 154.2, and then our sample size is 25. So this time, the question is asking for a 90% confidence interval. So we will have a narrower margin of error, and which means we have a narrower confidence interval, but we're giving up some of the confidence, right? We're not as confident. So we're going to be right 90% of the time, right? But 10% might not be. So there is that trade-off. So let's try and work through this together. Which Z would we use? What's the Z? Now we could, yeah, 1.645, and I'm just going to scroll up to see where that was. There should be a table here, right here. So 1.645 corresponds to 90% confidence level C. If you want, the question had to set a 99% confidence interval, then Z star would be 2.576. Okay. So that's correct, 1.645. Good. And this here is the sample mean. This is X bar. This is the standard deviation. There's our N. We have everything we need. So we could just go a 90% confidence interval. That's the mean mu. Fuel cost is X bar plus or minus the margin of error. Just to let you know how it all works, plus or minus. I'm giving lots of steps here so that everyone sees how it works. That's going to be, I'm going to make the equals down here so I have lots of room. It's going to be 330.6 plus or minus 1.645 times 154.2 divide by the square root of 25. that's going to equal 330.6 plus or minus. I like to do the margin of error because sometimes it's left in this format. It's just 300, like it's just estimate plus or minus the margin of error. Sometimes we just leave it in that. So I get 50.7318. So sometimes you'll see this in the textbook too, and in the assessments. It'll be in this format: estimate, which is 330.6, plus or minus margin of error, which is 50.738. It can be left like that. If the answer is showing the min to the max, then you need to unravel it by doing the subtraction and the addition. So we'll go down one more. That'll be 330.6 subtract 50.7318 to 330.6 plus 50.7318. And that ends up being 279.8682 to the maximum, which is 381.3318. And that also can go like this: 279.8682, comma 381.3318. So there's many ways to see these confidence intervals, how they can be shown. I'm just going to put boxes around the different ways. Sometimes we see it like this format. Sometimes we see it like this. And sometimes we see the range in brackets. 3 different ways to view the confidence intervals. They're all equivalent. They all mean the same thing. It's just 3 different presentations. They're all the same though. So a 90% confidence interval for the true mean mu fuel cost is 279.8682 to 381.3318. Does anybody have any questions on that, or see if I wrote anything down incorrectly? I believe it's all correct. But if you see anything, let me know. It looks good. Okay, so what I think. Okay, so let's do the ice cream example. This is a quality control one. So just think of a factory making lots of ice cream bars, right? And on the ice cream bars, each package says they are 86 grams. This is how the company advertises them, as being 86 grams. And so they need to be truthful about it, right? Canada Food Inspection Agency comes along, they do some confidence intervals, and that 86 better be in the range of plausible values, right? That's what a confidence interval is. It's a range of plausible values. So if they have 86, if they're going under, they're potentially ripping off the consumer, you and I. Or if they're going over, they are losing money potentially because it's not what it says on the package, and their price has been built into that. So yeah, it's good for everybody to be concerned about this for protection. So everything you drink, I'm trying to see, there's no bottles of water, but usually they say how much is in the bottle of water and the nutrition content, right? Every package usually if you think of the packages, actually you have a package there. Does that have nutrition on it, Catherine? Nutrition level? All that stuff goes through, yeah. So like you know the nutrition, that they're mandated to show like how many, whether the calories are and how many vitamin B, or is it fiber and all that. So they run these tests. They run these confidence intervals to make sure that it's being sold as stated, as advertised. Otherwise, it's misleading, and they do get fined. There's been cases where they have been fined. They're easy to find too. You can do a search to see who was in trouble last, and usually they'll pay the fine and then they'll have a sale to try to save their reputation. So anyways, so we have these ice cream bars. Pretend that, well, not pretend, let's just say we did an SRS of 16 ice cream bars. And let's say the sample mean, now make sure we're matching these up. That sample mean is X bar. So you want to match the words to the notation. So we assume that the weight of the ice cream bars has a normal distribution with an unknown mean and standard deviation sigma. So that's sigma 2 grams, right? So calculate a 95% confidence interval. So 95% confidence interval for the population mean weight of the ice cream bars. And then we need to draw a conclusion. Should the company be concerned if the ice cream packages say 86? So let's see how it works. Which Z are we going to use? Everybody in the room should have it memorized. We should know this one, right? Yes. 1.96. We all need to know that one, right? Because 95% is the most common that you'll see. So 1.96, right? 1.96. Very close to 2, right? Our empirical rule was mu plus or minus 2 was 95%, right? Of the area under the curve. Very close, but using the table, as we discussed, it's more precise to have 1.96. It's very close. And we'll put all these pieces together and we will say it like this. 95% confidence interval for the population mean mu. That means all ice cream bars. Right? Is, and I should put weight. Weight, it's the weight that we're doing here, is, because it's the average weight. It's the average weight that's advertised, 86 grams. And I think this one was taken from Dairy Queen. You know how they make they sell the bars? There's like the dilly bars and then there's the other bars. Yeah, I think it came from there. Okay, so we will do X bar plus or minus RZ times our sigma over square root n. And we'll just plug those in. The average mean was 85.1. That's up here, right? From the 16 bars that were, remember when they do these quality controls, they destroy them, right? So it's expensive too. They have to open them up and put them on a scale and they're done. They can't be sold because they get destroyed. So it can get expensive, especially when they're doing safety things for cars. They have to destroy a car, or they have to, what are those things? Airbags, when they test the airbags to make sure that they get deployed and all that, they're running all the stats. They have to deploy them so they get wrecked. You can't be used again, right? So this gets expensive, but it has to be done because it protects you and I. So 85.1 goes there. Plus or minus 1.96, there's our 1.96, multiplied by standard deviation, there is 2. I put brackets so that I don't run the numbers together. Just put a bracket around that. Divide by the square root of 16. Good. which equals 85.1 plus or minus, that all boils down to 0.98. If the question only asked, what's the margin of error? You don't give all this. You literally say the margin of error is 0.98 to demonstrate that you know what the margin of error part is, right? So the margin of error is 0.98, but we're going to keep going because it asked for the full confidence interval. This ends up being 84.12. So if I take 85.1 and I subtract 0.98, I get 84.12. And if I take 85.1 and add 0.98, I get 86.08 grams, because we're in weight here. Grams. Should the company be worried? So we've constructed our confidence interval for all the ice creams. We only took a sample of 16, but we're drawing inference on the whole population here. We're assuming that the confidence interval, that the weights of the ice creams are normally distributed, and that the true population standard deviation sigma is 2. We plug in all of our values. We're using Z of 1.96, and we come up with a range of values from 84.12 to 86.08. Should the company be worried or concerned? Or should they be relieved? I don't know. What would you say? Yeah, they're happy. They're going. The manager's going, okay, we're good. We're good. Why? Because 86 is in that range and it's a plausible value. So if you want to draw it, you can think of it like here, like a number line. And so our number line would go from there to there. 84.12 would be down here. 86.08 is here. The middle is always our X bar, which was 85.1. The center of our confidence intervals are always the X bar. Okay. So they should be okay. 86 is in there. 86 would be maybe here. Maybe. So should the company be worried? Answer, no. And you can put in the 86 grams is within the range of values. So it's contained inside 86. It's the high cholesterol example. So we take a random sample of 400 patients or subjects with high cholesterol using a new drug. After 2 months of taking the drug, the average decrease in cholesterol level, say, is 90. The researcher assumes the decrease in cholesterol is normally distributed with an unknown mean. That's what we're going to do the confidence interval for, and a standard deviation equal to 30. So that would be sigma here. And this 90 would be our X bar, right? Part of the process of writing these out is knowing how to match the words to the notation. And then 400 subjects, this would be our N. So this time we're going to do a 99. What would be our critical value Z star? Yes. Perfect. Yes, 2.576. And if you're wondering where we get it, if you came in a few minutes late, we get it from slide 8. There it is right there. 99%, 2.576. It's going to give us a wider confidence interval, a higher margin of error, but we have a higher confidence level. We're at 99%. So there's that trade-off. We get more confidence, but we have to have a wider confidence interval. So it's less precise, so. Okay, so we can do this with a 99% confidence interval for the true, and when I say the true, I mean the population, the true mu decrease. So the true mean, the true mean, that's the mean. Let me make it so you can see that clearly. Decrease in cholesterol is, and then we write it out, X bar plus or minus. And we have all these pieces. We know N, we know sigma, we know Z, we know X bar, and we just simply plug them in and we have our range of values. So we're going to start with X bar. Try to work along with me. Again, be honest with yourself. If you were not happy with your midterm grade and you're just not writing, this is one way to get your increase your knowledge, is by writing it down. 90 plus or minus 2.576 times sigma, which is 30, divide by square root, this time square root of, perfect, 400, yes. Which equals 90 plus or minus 3.864, which equals 86.136. And so I'm subtracting that to get that, and then I'm adding, so I will take 90, subtract 3.864, gives me 86.136. And then if I take 90 and I add that, I add 3.864, I get 93.864.